All right, so we're right about nearly at 9:30. I'd like to introduce the next session, which will be John Morris talking about his Applesauce hardware and the WOZ disk image format. Take it away, John.
Okay. Oh, yeah, it sounds like it's working. Okay, this year, I've actually done a few slides. Not many, but I do have some. My mom yelled at me for the last one, so. But I am still wearing shorts, so she's not going to like that either. Okay, we'll just do a quick recap for those who don't know. What is Applesauce? It's a high-resolution floppy drive controller. Lets you connect a disk up to a modern machine via USB. With it, you can send various commands to it, tell it to grab bits, but you can also tell it to be grabbing timing of flux streams and reading very detailed information off of the disk. So yeah. So started this in April of last year. Took about a month and a half to actually get disk imaging happening. Then I showed it off at KansasFest last year. And so, what has happened with it since then? Been doing a whole lot of code cleanup, redoing the hardware a few times, had some good smoking events, things like that. So, got it all kind of put together. And once I was very confident in the fact that, yes, we can actually grab everything we need off of this, it kind of turned into, now that we can capture the bits, how do we know that the bits are correct? You know, all these disks are starting to fail. You know, what is good, what is bad? The other part of the problem that we had was, now that we got all these bits that encompass far more data than what we've been able to have before, what do we actually put this in? You know, nib files can't contain the information, DSKs can't contain the information, EDDs can't contain the information, so something new needed to be created, which was the WOZ format, which I'll be talking about shortly. And basically, to prove all of this stuff out, I needed some people to give me a hand creating images. I have a few disks, but I needed lots of disks. I needed to be able to vet it across a huge amount of stuff, and came up with a couple of people. Stefan Rock and Antoine Vigneault were the main contributors. Those guys came up with almost 5,000 disk images between themselves that were imaged with Applesauce. So, yeah, there's about 200 gigabytes worth of images on the server that we've been using as test data, which will all be released very soon. We'll be talking about that a bit later too. So, created the WOZ files. WOZ files with the hat tip to Jason Scott for the name WOZ, because mine was really lame. Basically, in analyzing all these disks and how the protection works and what exactly can be transmitted from a disk into the machine, came up with a format that can basically encompass any structure of the disk, spiral tracking, you know, regular sectors, weak bits, in anything that can exist on a floppy can exist within a WOZ. Part of that, though, is a lot of the emulation that was going on was fairly naive in terms of it would just kind of grab the data from it and use it. You know, grab data from the disk image, process it, and just kind of runs it through. The simple fact of the matter is a lot of copy protection didn't rely truly on what data was there. It relied more on what data wasn't there. And due to idiosyncrasies within the drive, there was a lot of exploits of having a lot of nothing, so there's randomness flowing in and all these things. And so the WOZ turned from just a simple file format container into actually a large specification of this is how you need to treat the data within the containers. You know, to replicate the oddities of it. You know, there's a lot of funny stuff that goes on, you know, like the ability to tell a drive to turn its motor off that actually gives you data. You know, there's so many paths that protections used in order to stop things like boot tracing. You know, so you could actually read the data off of a disk by telling the disk to turn itself off repeatedly. You know, the little tricks like that basically needed to be specified out so that emulator developers could look at this and be, okay, that's really weird, let's put that in. Okay? So we got this specification put together about, it was like January or so. Kind of threw it out to the internet to have people eviscerate it and shame me. But it went pretty well, you know, we got a lot of useful feedback. And we basically were able to kind of lock down a file format, and then kind of began a lot of the process of, it turned into a social project, because it wasn't so much, you know, coming up with a file format and all that stuff. That's kind of straightforward. One of the harder parts is, how do we actually convince people to use this? People don't like change. Everyone's kind of happy with the DSKs they have and what's sitting out there. So then became basically like, okay, I guess I'm going to get a Twitter account now to start talking about this stuff, because it's like I need to kind of explain to everybody what the benefits were for being able to adopt this. You know, what it's bringing to the table. That went fairly well. I got a couple of people that were willing to basically put support into emulators. The first was with Virtual 2. He got a lot of it together, and then he went on a super cool vacation. And so that kind of delayed things a little bit. And so I jumped in to Open Emulator, which really has a very good existing disk emulation and basically built-in WOZ support to it, just so that I could kind of prove out that, yes, in fact, we can create WOZ images that contain the copy protection and are accurate enough that when you run the software, it passes its own copy protection checks. So we can make bit accurate images without the need to crack them. After getting Open Emulator out and being able to show, yes, all of this craziness actually does work, more emulator developers started following suit. Gerard came back and finished up the Virtual 2 support. There's support in MAME, Micro M8. There's a few more that are on the way, a couple that are on the fence still if they want to support it. And there's hardware support coming. So there's some new floppy emulators on the horizon that will also be able to run WOZ files. Okay, I guess I'm doing a demo now. Let's see, how do I turn that part off?
Do you know if Applewin is going to support WOZ files?
There has been discussion on that. We've been going back and forth.
So that's probably the biggest Windows.
Yeah, right now, in the discussion, basically they bring in nibbles at a time, and when you're running the disk, normally it sits in a loop waiting for the nibbles to come in off of the disk, which usually takes 32 CPU cycles. The way they do it is every time you hit the latch, it just gives you the next data. So they have very, very fast loading of disk images. they feel that the fast loading of disk images is a higher priority than accurate emulation of disk images. And so there's discussion about them implementing it, but they're not sure how they actually want to do it and whether they feel that their target audience would be more interested in having disks load fast or having WOZ support.
You mentioned the disk access speed and Virtual 2, which does have the .WOZ support. Virtual 2, even the current version with the WOZ support, you can still put it on, speed setting 3, and disk access is almost instantaneous.
Yes.
So do you know, is there something about the Apple One's disk implementation that's making it so, an extra challenge to have both fast and WOZ support at the same time?
I do not know that.
Okay.
I try to jump in and just support
Sure.
developers as much as possible. If they want to support it, fantastic. If they don't, well, that's cool too. So I've been having discussions with them, talking about, how they could arrange it and stuff. But yeah, so far, nothing has kind of come of it. It's been just conversations. So, yep.
Isn't it true your Applesauce program will output disk images along with WOZ images?
DSKs?
DSK?
Yes, it will. From the fast imager, you can output DSKs. You can even open DSKs and look at all the data in them and stuff like that. So DSK is, there's a lot of talk of WOZ replacing everything. And I just simply don't agree with that. I think DSKs themselves are extremely useful. They're very good for what they do. You aren't going to stick bit accurate images in them, but they do. They serve a very useful purpose, and so I'm very much, don't believe in WOZ replacing DSKs. Nibs, go away. Die in fire. Those are just horrific. So, yeah, WOZ should definitely be killing those. But yeah, no, DSKs, thumbs up from me. I still like them. There's a lot of hardware that still only uses DSKs. We can't sit down and, say, hey, let's get rid of this. That's ludicrous. So, okay, these windows are a lot different here. Okay, we'll open up some Virtual 2 here. And, well, here, let's just start right at the top here. So this is a WOZ file of Archon. WOZ files tend to run about Archon's 227K. They normally run about 233K for a full disk. Archon has a funky copy protection scheme in that tracks 5 and 6 are actually written on a drive with a head that is 2 tracks wide. So it is bit aligned for this giant swath across the disk. And what they do is they look at this disk and they start reading it and they sweep the head back and forth across this area. And as long as everything still checksums, then they let you run. So it's pretty ingenious stuff. Okay, open please. Okay, well, you're not gonna let me do it like that. Here's sound.
This Virtual 2, it makes drive noises.
Uh-huh. Well, if there's sound, but
Do
it
the drive
doesn't.
noises
Yeah, if you put
sound
sound,
like
it
the
will.
same?
I don't see sound.
They do.
Yeah.
I can answer that in the affirmative at least.
Yes. Yeah. So for some reason, I guess there's no speakers for playing sound here. So, because it's a projector. But yeah, basically when it runs, before it gets to this screen, you can actually, it does its loading, and then you hear it go like, as it, does a really quick scan across the protected area. but we are at the point where we have already passed the protection, which is pretty boring, but. Okay. Let's get something more fun. It's a lot more interesting when you can actually like hear it. Weird that doesn't want to let me. Right. Okay. Anyway, let's.
Is the sound on your computer not playing? Because we can put a microphone up there.
Well, no, I don't hear it coming out of here either. So,
That might be your plugin you're using, perhaps. I don't know.
yeah, I'm not sure. That's good. So this protection for Blazing Paddles Vaudeville had an interesting way of having tracks be very hard aligned. And what it does is it starts loading and then it runs down through a whole bunch of tracks and makes sure that all of the tracks are actually lined up. Because there's no synchronization on a stock disc 2, so you can't actually be able to make copies and line them up on the device. Well, not easily. Copy programs tried, but sometimes they'd get it, sometimes they wouldn't. And there's Blazing Paddles. Passed its protection check again. And so basically, yeah, it's Dino eggs is a fun one.
John, can we launch some of those images with the projector disconnected and with the microphone up to the audio just so we can hear it?
Well, wait, maybe.
Speakers?
The projector is shutting off his audio because it's not an audio device. Same thing was happening.
Some
with the-
projectors are.
Yeah.
Go
It gave him, when he tried to turn up his volume, it gave him the
system preferences. You might be able to
just
tell the sound
unplug
to
the
go
projector and his audio will come back.
So, output.
internal speakers.
No, or do that.
There.
He's got it, Ken.
Okay. Because it has.
The sound turned up.
Let's try something.
No, it's pretty good.
Here, we'll try Archon again. Well, let's. Okay. Thank you.
Projector and speakers.
For the really quick
Yeah.
click. That was its protection check, just running through the tracks and making sure that everything is lined up. And what else is there? Oh, Hard Hat Mac. That's always a fun one too. One of my favorites. One of Javier's favorites too.
Yep.
And we're in. Okay, I'm just gonna play this for a little while. Okay, no, I'm not. So, yeah, basically, we're able to run images that pass their checks. So, bit accurate disk images than WOZ files. Okay. And I guess we will look at the actual Applesauce software as well. Give that a quick test drive here. Okay, so within Applesauce, there's a few different styles of imaging. We have the fast disk imager, which is based for unprotected disks. It's let's grab the data as quickly as we possibly can, which runs about 12 seconds or so. Luckily, I do have a disk in the drive, so, because I didn't bring any down with me. And that's the boring imaging of a disk. So then you can save that. You can save it as a WOZ, or you can save it as a DSK. Either way you want to go. This is just going to be, it basically will work for 16 sector. It'll also do 13 sector disks. Not many emulators actually support 13 sector. Open Emulator and stuff does. But yeah, so discard that. Then we have the Flux Imager. Flux Imager is a little bit beefier. It also allows you to be entering metadata. Maybe I'll scoot this one away for a little bit. So this is now going quarter track by quarter track. What it's displaying is the brighter the color, the higher the density of flux transitions within that area. So it's going to be basically highlighting things like sync fields and stuff like that, and kind of giving texture for the data that you have in there. And while it's imaging, you can sit down and enter in all of your metadata, which is fun because, well, the disk is in the drive and you need to kind of transpose what's on the label. But if you're thinking ahead, this works out really well. Imaging of a disk usually takes about 4 minutes. It does it in a 2-pass system. So it is currently doing the first pass where it is grabbing a single copy of every quarter track. Once it does that, it kind of looks at the data, figures out where data actually exists. So, a lot of disks will have unformatted tracks and stuff like that, for protections and stuff. And so it knows to actually just, skip those. Second pass, it goes in, and now it is fetching extra copies of everything that it found. So whenever it's looking, since it's grabbing quarter tracks, you can kind of see the written track, and then you kind of have a shadow in each of the quarter tracks next to it that is, a shadow of the track. Because the head is a little bit wider than the quarter track that's written. So what this is doing is it's going and grabbing an additional 4 copies of every written track and 2 additional copies of every shadow. So it has a lot of different views of the data because it just wants to make sure that it gets everything that's on there.
I'm sorry, this does work with 40 track discs?
No, it does not work with
It's
40
not,
track.
okay.
Because I'd have to change the picture. That's a lot of work. Theoretically, yes, it could. The software itself will it'll only try to move the head through 36.
Okay.
So it could easily be changed to say, hey, go to 40, and it would be fine doing that. I don't know if we want to finish watching this or not. We'll just stop it. So we have that. There is the disk writer. Currently, the disk writer actually only works with DSKs. I'm looking at adding in WOZ support for it still, but there's a lot of complexities with it. Things like like Archon for their 2-track wide track. A disk 2 simply cannot write that. There's a huge percentage of disks that Applesauce can write correctly out of a WOZ. But there are going to be cases where it simply cannot do it. You know, we do not have access to the level of hardware that they do.
Would it be possible to create a disk, like a universal writing disk, that would do all those things
A drive for that?
for all the protections? Or?
Theoretically, but it'd probably be insanely expensive. You know, getting heads and stuff manufactured would probably be cost prohibitive. Let's see, I think we got here, DSK Wavy Navy. So we'll just overwrite this disk. So we've loaded in the DSK. We hit write disk. It basically starts looking at the disk, tries to figure out how it should structure the data on it, the timings of it and stuff. And then it does writes and verifies on it.
So it writes pretty fast.
Yeah, it's not too bad. It's going through all the verification and stuff too. So this is a Apple II compatible disk now that has Wavy Navy on it. Should have brought Apple II. Could have actually booted it. There's also calibration. I have some ideas for a couple other calibrations that I want to do. The first one I have actually is just a speed test. It actually uses the sensor that you have in there, so it doesn't actually need to have a floppy in it to tell how fast the drive is spinning. But if it doesn't have a sensor, it will write to the disk and use that to track the speed. And then there's the 3470 noise analysis, which, unless you're really nerdy, you're probably not going to need to get in here. But basically, it looks at the quality of the 3470 chip that you have in there, which can make it easier to image some styles of copy protection, you know. So that's
What is that chip, John? What does it do?
the 3470 chip is the chip that sits between the head and the data that's coming in from the drive. So it translates, every time it basically sees a flux transition on the disk, it sends out a pulse to say, I saw a 1. Because disks don't actually contain ones and zeros, you know, bits as we think of them. They actually only contain ones, and they contain space between the ones. And the amount of time that exists between the ones determines how many zeros actually should be there. So when it's making a bit stream, it's actually sitting down and saying 1, 1, 1, 1, 1, 1, 1. And it looks at the time between that and says, okay, well, wherever it delayed, that's where zeros are getting inserted. And that's what creates a stream. When a lot of copy protections, what they would do is create long streams of nothingness. And when you have a long stream of nothingness, what the MC3470 chip does is it's looking for these ones and doesn't see them. And so it has a little amplifier in it, and it turns up its amplifier going, I can't quite read the disk. Let's try to adjust this so that I can read the disk better. And it keeps turning itself up and turning itself up until it goes to 11. And it freaks out and just, starts tripping out and thinking that it is seeing ones. And so it starts firing something, it fires a bit, so, I see it. And then it changes its mind and goes, I don't actually see it. We're calling that another transition. And it freaks out, which is why data on a disk is, encoded in nibbles, because you're never supposed to have more than 2 zeros in a row, which is about 8 microseconds, or else the 3470 has an acid trip and goes nutty on you. So a lot of copy protections use that to their advantage, because when you have a disk with nothing, when you actually have values around it, you can read it and you can say, okay, now what exists here? And it knows that 3470 is just going to be throwing up because there is no transitions there. So it's throwing all these random data out as it's tripping. Comes back around, looks at it again. Hey, the data on the disk is different this time. Look at it again. Hey, it's still different. So they can exploit the fact that it's having a bad time because it's failing at its job by looking at these things changing. But when you hit it with a bit copier, the bit copier runs through and it sees this and it thinks, oh, this is data, and it writes that out. It's like, I'm copying this stuff. We figured out what bits they have. But now when the program runs, it comes through and goes, okay, here's the values. Okay, next time through, hey, the values are the same. Next time through, okay, this isn't changing anymore. We got a copy. And they can shut it down. So one of the things that Applesauce does is when it's doing its analysis of the Flux images, it can actually detect where they have written these zero gaps and can see, where things are freaking out and be able to say, okay, let's clean all of these. And when it writes out the WOZ file, it actually writes it out as a zero space. And within the emulation side, within the WOZ spec, it says, once you get 3 zeros, you need to start freaking out too. And so then that way, when you're emulating on the WOZ, it hits those zeros, it throws the fake bits, and the randomness is there. So the 3470 noise analysis basically empties out tracks. It puts everything to no transitions. And then it looks and maps out how much noise is coming out of it, how much it is freaking out, because there are different behaviors for it. And some chips can be so noisy that they actually create real nibbles, just because it's firing so much. And so you try to actually get something that's putting as little data as possible out there. So you could run this to find things that have low numbers and be able to use that to better image things because it's less data to analyze, but therefore it's less opportunity for it to miss a spot.
Click the button. Click the button.
Okay, well it's gonna, yeah, we can erase this disk, sure.
John?
Mm-hmm.
Quick question related to this topic about the MC3470 freaking out when it has just one space of zeros.
Mm-hmm.
And now that the emulators are gradually adopting that, do you know if that's going to change any of the existing methods for detecting when an emulator is active? I kind of vaguely recall that the emulator detection was kind of relying on the fact that the emulators were not freaking out in those situations.
Yeah, I think it will make it a little bit more challenging in some cases, but within the WOZ spec itself, I don't actually specify how you should be sending out these bits. I don't specify like, hey, there's a pattern. I have a couple of suggestions for like, if you're on a, software emulation, doesn't matter. When you get into more hardware stuff where you're more constrained in terms of performance and stuff, I have a couple of techniques to help you gain some performance in sending these out, but I never say what they should be. So sometimes some emulators are doing it as, true random, and it's throwing things out randomly. Others are actually they just have a buffer of random data and they just cycle through it. So, I do think that it can actually be used to still potentially detect when emulators are running. But there's actually a lot of you know, whenever that conversation comes up, and then everyone's just like, well, we're going to make it so we can't be detected. So, you know, it's kind of like the whole copy protection
Yeah.
race all over again.
And I know you're not writing the emulators, but as a software developer, you know, I just generally advocate to the community that being able to detect the emulator is a good thing, because then software developers, when you know they run into differences between the way one emulator and another handles it, or versus real hardware, which does happen, you know, then you know in our software we can put in some workarounds to make sure that it does work on all platforms.
Mhm.
Whereas without that ability to detect the emulator, sometimes we just can get backed into a corner.
Yeah, yeah, absolutely. So this particular chip here it's nothing amazing. Basically, having under about 15,000 here tends to work out pretty well. You know, we have some drives that are down, you know, under 100, but you have some that are also up 30,000 plus. So, you know, those ones just generate so much noise. You know, this is so basically the number, the 14,855, is the number of bits that it's an average of the number of bits that are thrown for each revolution of the disk. So each time it goes around, it's throwing right there. One of the interesting things about this is, for something that's random, that line sure is flat. You know, and it's consistent, and different chips will show the same thing. So, you know, in terms of being random, it's actually pretty terrible, because it fits with, you know, it's all within a certain area. But that's just how the 3470s work.
John?
Mm-hmm.
So if you have an old disk that was created on a drive where the belt might have been failing, so you have speed differences, would it be able to find the sectors?
Would, from the Flux image?
Yeah, if you put that old disk in and it was written badly, there may be certain sectors where the speed was off.
Yeah, I mean, it depends on how far the speed is off. You know, if the bits are coming in too slow, then it will be inserting zeros in there. But part of what Applesauce also does, if the track is kind of consistently at a rate, you know, when it does like the analysis of the Flux image, it doesn't actually ever look at a window of being 4 microseconds. What it actually does is it actually looks at the entire stream, and then it says, okay, for the average timings, you know, it actually looks at the clockings of all these things and says, okay, well, a 1-1 is right about this time. A 1-0-1 is about this time. Because it's, you know, it's a valid 1-1 sequence can be anywhere from like 2.5 microseconds actually up to like 5 point something microseconds. It's actually a fairly large window, because these drives are horribly inaccurate. You know, when you actually look at the true timings that like the Applesauce grabs, you can see the drive motor fluctuating. You know, so for a track that is written really slowly, it will look at that and retime the 1-1 sequence based on what it finds on the disk, and it would calibrate to that and actually construct the stream off of that. So if the drive was too slow, it would be able to reconstruct it, as well as if it was too fast, it would still be able to, but within tolerances. You know, you can't double the speed of it and have it, you know, still figure that out. Okay.
Well, I have old disks like that. I get it to 4 a.m.
The other portion of Applesauce, so basically, you know, you have imaging here. Imaging is kind of a completely separate function from generation of WOZ files. So, you know, the imaging process the Flux imaging process will create A2R files. which are Apple II RAW files, which run about 20 megabytes for a single disk. This is where it's grabbing the multiple passes and all that stuff. So it just, it gathers quite a bit of data about it because it's not keeping bits. It's keeping the number of nanoseconds that exists between flux transitions. So it's a large data set. To actually, let me find some data here. To actually be able to create a WOZ file on here, let's do Kato, I've done that. You tell it to open up an A2R. This will open up all kinds of files. It'll open up EDDs, it'll open up, DSKs. I think I took out nibs. I think I was mad at them or something. But, okay, so this window's really big. So what it's doing here, this is basically the track layout. This is it trying to construct the disk. Now it is actually going through and validating what is on the disk. So when a disk comes in, it doesn't try to understand it doesn't have preconceived notions really of what the structure of the disk is. It uses a bit of a machine learning algorithm to actually analyze and find structure, and it understands things like 16 sector, 13 sector, address fields, data fields, stuff like that. It makes no assumptions about things like prologues, epilogues, what their values should be, what their sizes should be, anything like that. Oh, okay. And so what this does is now actually gone through the entire disk. This figured out where things are. It matches up tracks next to each other to be able to merge in quarter track data. It was executing repairs, stitching together the best track that it possibly could for each one, and validated. It basically it's reverse engineers the RWTS to figure out what kind of checksums they're using, if there are some, and then runs its simulated RWTS against the disk. This view shows a highlighting of what it found in its structure, and basically it's determined that this is a 16 sector. It's D5A96. The green is the checksum. It's actually using an epilogue of just AF, which is very non-standard, but okay. These are actually gaps that exist within the disk that they're writing out. Could be some kind of weak bit thing, but I don't think that's what they're using. And it will basically just kind of rip apart all the data, show you the structure, to let you be able to look at it and parse it and explore and enjoy. And it's some amazing stuff when you get in there and actually look at some of the protections. Things like E7 protections, you can actually see it laid out as the E7s and see all the stop bits in the middle and all that kind of stuff. So after it's done this, basically it says that it has a good disk here. You can output a WOZ file from it. And from the WOZ, let's talk real fast. Well, I'm gonna rush here. Oh, I suppose I can turn up the speed on this. Maybe. Oh, well, great. And we have a bit accurate copy of Kato.
Yeah.
Okay, and that's it. Any other quick questions or?
So are there ever cases where, you do the Flux Imager and then you just can't write out a WOZ for some reason? Like maybe not because of damage, but because of copy protection or something? You just got to.
Yeah. So the Applesauce software is still very much under construction. I'm continuously working on the recognizers, getting all that stuff. So there are structures that it does understand and can do very well, and there are a lot still that it does not understand yet. So I still need to work things, things Spirodisk and a lot of this kind of stuff. There's still work to do on that front. So, it's by no means done, but it's all doable.
So if a disk fails, would you recommend saving it as the A2R and uploading that to
Yes.
wherever
Yes.
Asimov? And
Yeah, so I have the A2R versus the WOZ separated just for this. So you can keep grabbing A2Rs. I have A2Rs that I grabbed at KansasFest last year that I couldn't do then, that I can do it now. So there's going to be a process to basically be, as long as you have A2Rs, you'll be able to cut a WOZ. So even if there's like, an error in the generation of WOZ files, when that bug is fixed, you can actually regenerate the WOZ files from the A2Rs and not have to re-image.
With personal unprotected disks, are you still recommending the fast disk imager with its repair routines versus doing a Flux image?
Yeah.
Okay.
Yeah, the Flux image, it's great, but if it's just data, there's no reason to go through that.
So for the path to 3.5-inch support, is it a known quantity at this point, or you still have unresolved issues to address?
3.5 support, I'm successfully talking to the drives, can move the head, grab bits. Now I'm looking at how exactly I need to be storing the data and what processing that I need to do for it. So basically I'm diving into how are these disks protected, what systems are they using, and need to build the system to actually check that stuff.
And the WOZ format hold a 3.5-inch disk?
Yes, it will.
As far as the software goes, are there any real functions of the Applesauce software that would be useful to someone who doesn't have the Applesauce hardware?
The disk image opening, so being able to open up A2Rs, you can kind of jump in, be able to explore, look at it. You can cut WOZs out of it. It makes a great viewer. You can also, be able to open other file types with other disk image types with it too, but it is still just, nibble layout, so it doesn't try to interpret ProDOS, anything like that.
Well, it's time to stop. We have a 15-minute break until 10:30. If you have other questions, you can certainly come up and ask them. And be back here at 10:30 for information about the Micro M8 or Micro Mate emulator.